Non-Mendelian traits. This is your genetic notes, day 2, and Mendel discovered the basic rules of dominant and recessive, but not everything works with only 2 possible forms. We know that skin color comes in a whole variety of shades, so does eye color, and there's even some organisms where there's a blending effect that occurs. When a red and a white snapdragon mate, we end up with pink. So there's other rules besides just basic dominant recessive, and anything that works in any way different is called a non-Mendelian trait, since Mendel discovered the basic rules. We call those Mendel's, dominant and recessive. So the first we're going to look at is considered sex-linked. And sex-linked is anything that is found on the sex chromosomes and therefore will affect men and women differently. So you know that all humans inherit 23 chromosomes, and they come in these pairs. One comes from mom and one comes from dad. And these pairs of chromosomes that have the same genes but possibly different alleles are called homologous chromosomes. So this one might have the recessive gene for, say, tongue rolling that came from mom, and dad may have donated the dominant allele for tongue rolling. So the first 22 pairs rather, are all exactly the same. Same genes, same size, and we call those autosomes. So these are just the regular chromosomes that code for regular body traits, and everyone receives 2 copies of each. But you'll notice this last pair at the end is a non-match, and that's because this is a male, and these are the sex chromosomes. So if you inherit 2 X's, you would be a female, and if you have a non-matching pair, that would be an X, and this is considered a Y, even though it's not, none of these are X-shaped really. That means you are a male, and the genes that are on this Y chromosome essentially control the development during the time that you were in your mother's womb and prevent you from becoming female and instead change your biology into maleness if you inherit these genes. So this last 23rd pair are called sex chromosomes because they determine gender, and the rest of them are called auto or self chromosomes. If you have a trait that's found on one of those sex chromosomes, like hemophilia, you're going to end up with men being affected generally more commonly. So hemophilia is a bleeding disorder because you are lacking a protein, so there's a mutation on one of the alleles where that protein that would normally help you to form a blood clot right here and stop the bleeding, instead you have much less of that blood clotting factor. So you can see here the clotting factor is patching the cut and the blood flow slows down. You have a little fibrin mesh that serves like a little cork essentially, or a little screen, and that stops the bleeding that then would become a scab. But if you have hemophilia, you do not make enough of that protein, and then you just really continue to bleed much longer than you would normally, and it is potentially life-threatening, especially if there's an internal injury that might normally just give you a bad bruise, could bleed continuously on the inside, especially something like maybe even a minor fall or a car accident that normally people would walk away from. So hemophilia is a recessive allele, and it is found on the X sex chromosomes. So if you're a woman, you're going to get 2 copies, and you could get a dominant normal form, which means you're just fine, or you could get a recessive form, which means you would not produce the proper amount of protein. But as you know, if you have one of each, you would still show the dominant form and be normal. So this works pretty much the same as we've studied before for females because they get 2 copies. But if you are receiving 2 bad copies, you would be a hemophiliac, so that's a homozygous recessive. If you have 2 good copies, homozygous dominant, you're normal. And we consider the people who have the recessive allele but are normal and don't show that trait, they're carriers, as in they carry that allele and they can pass it on to their kids. Males, however, do not have that same setup. They do not get 2 X chromosomes, they only get 1. And the trait is on this X chromosome. So if they receive a Y and are therefore male and their other X chromosome is normal, then they'll be normal. But if their X chromosome carries the hemophiliac allele, even though they've only gotten one copy of it, unlike women that can get one copy and still be normal, there's no other X chromosome to provide the males with the proper protein. So the one allele that they get is going to actually determine their genotype, and their phenotype, and they will actually develop hemophilia. So males, because of this, are much, much more likely to be affected by any trait that's found on that X chromosome, because they show whatever it is that they inherit. There is a famous case of hemophilia, which again was a sex-linked trait. It started with Queen Victoria, who was an English queen, and when she had her children, one of her sons had hemophilia, and 2 or 3 of her daughters were carriers. And back in the day, and I think this is still somewhat true, the royal people married royal people of other countries to help establish relationships and power between those countries. So Queen Victoria spread her hemophiliac allele to the German, Spanish, and royal Russian families. Now this is a pretty famous royal family of Russia, the Tsar Nicholas and his Tsarina Alexandra, who was a carrier of hemophilia. They had a son, Alexis, who became hemophiliac. And you might be familiar with the famous Princess Anastasia. So this whole family was actually murdered by the Bolsheviks in the Russian Revolution that occurred. So they actually all died of war and not of hemophilia. So if we were looking at this family and the father was completely unaffected, normal gene, but the mother was also normal, but unbeknownst to her was a carrier, she would pass that allele down to 50% of her sons, right? She has a 50-50 chance. So out of the sons, half of them would be likely to have hemophilia. Whereas for the daughters that get an X chromosome from dad, both of them would inherit that X chromosome that has the dominant allele, and they would be fine. 50% of the daughters would receive the hemophiliac allele from mom, but they would still have the dominant one to cover it up. So none of the girls would be affected, but 50% of the boys would have the chance of being affected. Color blindness, red-green color blindness in specific, is also a sex-linked trait. And if you are looking at this little area of dots over here in the corner and you don't see a 29, that's a 2 and a 9, that would mean you probably have red-green color blindness. And again, it affects boys more than it affects girls. So if, again, we had a dad here who is normal and a mom, or her 2 possible gamete eggs and his gamete sperm, are going to match up in a Punnett square. The guys half of the time would donate their X chromosome and the other half would produce males and donate their Y chromosome. The moms half of the time would give her dominant allele and 50% of the time her recessive allele. So in looking at their possible children, here we have 50% girls and 50% boys. But of their girls, this one is normal, this one is also normal but a carrier, this one is normal, and that one is the colorblind male. So it's impossible for this particular couple match to have any daughters that are colorblind. But again, 50% of their boys would be affected. So anything that's on the Y chromosome would only affect males, but anything on that X chromosome is going to affect males more often than females, just because they only get one copy. So there are other traits, multiple alleles, multiple genes, blending genes, codominant genes, but this is just the first non-Mendelian trait called sex-linked.